Dynamic routing, we're talking about things like EIGRP, OSPF, BGP, ISIS, and so on. Those are our dynamic routing protocols. We're going to do a quick introduction to dynamic routing first. Then we're going to get into the specifics. I normally don't actually start EIGRP until Thursday. We might actually get to a bit of the introduction of EIGRP today. We're certainly going to be covering RIP today as well. You guys are going to actually configure RIP. Even though it's kind of a useless protocol, we still like to configure it because it gives us an idea of how protocols are configured in the future as well. All right? This is the timeline of our routing protocols. Notice that the first routing protocol came out in 1982. It was called the Exterior Gateway Protocol. It doesn't exist anymore, but that was our first routing protocol. And then Cisco developed very shortly after that an interior gateway routing protocol called IGRP. There's two things that are common with those two protocols. They were classful. They didn't do subnetting. They didn't support subnetting. So those two protocols actually have been deprecated. They don't really exist anymore because we don't like to use classful protocols. What is a classful protocol? What is a classful protocol?
It's set with its boundary of its class.
It's a protocol that doesn't understand subnetting, right? It has to route within its class boundary because it doesn't send the subnet mask information along with the routing updates, okay? So then we had RIP version 1 that came out in 1988. RIP version 1, also a classful routing protocol. And then we started to see the advent or the invention of our more modern protocols, ISIS, EIGRP, OSPF, RIP version 2, etc., etc. Okay? So if you look at the table at the bottom there, it gives you an idea of how we classify protocols. There are several different sub-classifications of routing protocols. You've got this concept of classful versus classless. Classless is good because that means we support subnetting. Classful is bad because we don't support subnetting. All right? You'll also see in the columns, we have two major columns, interior versus exterior. What is the difference between an interior protocol and an exterior protocol? Any ideas? What is an exterior protocol? Where is an exterior protocol used?
On the internet.
On the internet, right. Exterior protocols are used to route between autonomous systems, between enterprise networks. Interior routing protocols are used to route within your autonomous system or within your enterprise network. So if you can imagine, companies are going to be running an IGP inside their network. They'll be running an EGP outside the network, like BGP. BGP happens to be the only exterior gateway protocol that's in use today. Within the umbrella of interior, we also have two subclassifications, distance vector versus link state. And I'm going to describe to you guys in a little bit the difference between distance vector and link state. There is a pretty significant difference between those two types of protocols. And we'll take a look at what those differences are in a little bit. Okay? All right. So what is the benefit of using a routing protocol? First of all, why use a dynamic protocol as opposed to a static method? What do we gain from using a dynamic protocol as opposed to a static method?
You don't have to do manual updates if something changes.
You don't have to do manual updates when something changes, right? The whole concept of a dynamic protocol is it gives us the ability to dynamically recover or dynamically exchange information about the topology. If a network goes down, everybody learns that that network goes down. If a network is added, everybody learns that that network was added. Does that make sense? That is really what a dynamic protocol is all about. Maintaining an active database of all of the destination networks that exist within our enterprise. All right? So the purpose of a dynamic protocol is to discover new networks, to disseminate that information to other routers within the network, and to do it automatically. In addition, these protocols run something called an algorithm. That algorithm is used to calculate, the best path to a destination. So another function of a dynamic protocol is to calculate the destination. I'm going to move that so it's not in your way there. Okay.
No problem.
Okay. The purpose of the algorithm is to allow the protocol to make decisions on how to choose the best path. As we go through and look at each of these protocols, we're going to look at EIGRP, we're going to look at OSPF, we're going to look at RIP. We're going to understand how that algorithm works. I can teach you guys how to configure OSPF and EIGRP in probably an hour. But we're going to spend like 2 hours on each protocol. Because we're going to learn the theory behind the madness, right? We're going to learn how these protocols actually make decisions, and we're going to learn all the calculations that are required for those protocols to make their appropriate decisions. All right? When it comes to a dynamic protocol, there are a lot of things that happen on the back end. The protocols themselves exchange information. So if you're an EIGRP router and I'm an EIGRP router, we're actually speaking a language with each other, and we're exchanging messages and information between each other. Now, something has to happen to that data that's being exchanged between the two routers. This slide is kind of depicting the process of maintaining that information. We have data structures, we have routing protocol messages, and we have our algorithm. So let me break down the three differences here between a data structure, a routing protocol message, and an algorithm. And I'll try and do it in a way that is kind of easy to understand. There are three data structures that exist with routing protocols. A routing table is one of those data structures. And what goes into the routing table? What goes into a routing table? Routes. Routes, right? Not only just routes, the best routes. Agreed? So the routing table is considered to be a data structure. But the whole point of a dynamic protocol is that not only are you learning about the best route, but you're also learning about all the other possible routes that exist, right? I mean, that's the whole concept of dynamic routing. I have more than one path to a destination. I choose the best path, but I also need to know about the other paths that exist. So there's another data structure called a topology table. A topology table is a database of all of the paths that exist. So that's the second data structure. The first data structure we talked about, the routing table, that's the best path. The second data structure, the topology table, that's everything that I'm learning. And then the third data structure is a list of all of my information sources. What do I mean by information sources? What is an information source when it comes to dynamic routing? Another router, right? In the case of dynamic routing protocols, it's my neighbor router. So if I'm an EIGRP router and you're a neighbor and you're a neighbor, you guys are my information sources. You guys are the ones that are providing me routing information that I don't know about. That's the third data structure. a database of all my information sources. That data structure is called a neighbor table. You don't have to write all this down because we're going to see a specific reference to each of these data structures as we start to get into the protocols in detail. So if you imagine the process, right? What's the process? I configure a dynamic protocol. The first thing I do is I figure out who I'm getting information from, which are my neighbors. The second thing I do is I get all the information that they know. That's my topology. And the third thing I do is I run my algorithm against that topology database to extract the best routes to my destinations. So I want to extract the best routes to my destinations. I mean, ultimately, that's the goal of routing, isn't it? Pick the best route to a destination. That is the goal of routing. Pick the best route to a network destination. I know it seems like a lot of information. It is. But we're going to see this over and over again as we start to get into each of the protocols individually. So this is not the only time you're going to see a reference to these three things. Now the algorithm. So we talked about data structures. Let's go down to the algorithm. What is an algorithm? I mean, the general definition of algorithm is a computational process, right? It is a method for calculating something. Every routing protocol has its own method for calculating something. Ultimately, what's the goal of the algorithm? When it comes to a dynamic routing protocol, what is the ultimate goal of an algorithm?
Determine the best path.
To determine the best path. That's right. One of the things that you guys are going to have to know for the test is what protocols use what algorithms and how those decisions are made. We're going to learn that as we go through each of the protocols in the process of discussion here. Okay? So the last thing we talk about is routing protocol messages. The routing protocol messages are the message types that are used to facilitate the other two processes. I have to communicate to my neighbors in order to get the data structures. I have to communicate to my neighbors in order to pick my best path. Okay? So an example of a routing protocol message would be a hello packet. What do you think a hello packet might be used for within a routing protocol? To identify neighbors, to announce yourself as a neighbor, and to hear other routers as neighbors. That's one example of a routing protocol message, a hello packet. What about an update? An update is another type of routing protocol message. What would an update be used for?
Changes.
To exchange routing information. I'm going to update you with additional routing information. I'm going to update you with new routing information. Okay? There's 5 different message types that we're going to see. I'm not going to go through all 5 of them right now because they do differ slightly between EIGRP and OSPF. All right? Does everybody have at least a general understanding of what we're talking about here? Okay? You guys feel relatively comfortable with these concepts, right? Not specific to any protocol, but in general what these concepts represent. Okay? Because, trust me, the foundation is extremely important here. You have to have that foundation knowledge in order to understand everything else. So what is the advantage of a dynamic protocol? Well, we already kind of talked about that. The ability to learn about network changes automatically. See, if you're using static routes and a route changes or a route goes away, the router doesn't know about it. because the router simply does whatever you tell it to do. There are disadvantages to dynamic protocols, though. All of this stuff that we're talking about, routing protocol messages, algorithms, exchanging information, that equates to overhead. So routing protocols require the use of CPU cycles, memory to store all these data structures, CPU cycles to run the calculations, to pick the best path, and so on. So dynamic protocols do take more resources than static routing does. Dynamic protocols also tend to be less secure. Why is a dynamic protocol less secure than a static route?
It's a can be screwed with.
Anything that's dynamic can be manipulated. Somebody can inject routes or put false routes into your network. We're going to talk about how to set up these routing protocols, but we don't really talk about how to secure the routing protocols until we get to the CCNP level. All right? There are times when static routes are more appropriate. A default route is a perfect example. We use a default route to get to the internet because most routers that people own can't support 1 million routes in their database. So rather than do a dynamic process to exchange 1 million routes, we're going to use a static process and just use a default route. Did you guys ever heard the term stub network? What is a stub network? Any ideas? In general, what is a stub network? Anybody? It is a network that only has one way to get in and one way to go out. Okay?
Mina got it.
Yes, Mina got it. Absolutely. One way in and one way out. Why is it important to identify stub networks? Well, when you have a stub network, if there's only one way in and one way out, static routing is probably one of your better options because all routes are going to go to one destination as opposed to having multiple paths. Your home network is a stub network. Most people's home networks is a stub network, meaning that you only have one way to get to the internet. There's no need for you to have dynamic routing in your home network because you only have one network and there's only one way to get to the internet. So we just use static routes to get to the internet. All right? Stub routing is a very important concept. We'll talk more about stub routing as we get into the protocols a little bit later on. So what is the general operation of a dynamic protocol? Well, number one, discover neighbors. The very first thing that has to happen with any dynamic protocol is you have to figure out who your neighbors are. All right? You have to figure out who you're getting the information from. So when you enable a routing protocol on an interface, it starts sending and receiving hello packets on that interface. And that's how we identify our neighbors. Once we've established that adjacency with that neighbor, then we can start sharing routing information with that neighbor. We share routing information with that neighbor. I send that neighbor all the routes that I know about. That neighbor sends me all the routes that they know about. Once that information is exchanged, that goes into our topology database, and then we can start to calculate using the algorithm the best routes to destinations. Another function of a dynamic protocol, though, is to make sure that we understand when that stuff changes as well. If there's a change in the topology, we need to disseminate that information to the other routers in the network dynamically. What is the process called from the point when the change happens to the point where everybody knows about that change? Does anybody know what term we use to describe that? Yes. Lloyd got it correct. Yasmina got it correct. It's called convergence. Convergence. Everything comes together. Convergence, right? We use the term convergence kind of loosely in networking. A converged network architecture is a network that runs voice, video, and data. But convergence, we'll see convergence when we talk about spanning tree. We see convergence when we talk about BTP. We see convergence when we talk about routing protocols. The concept of convergence is how long does it take for when a change occurs in the topology that everybody's aware of that particular change. That is our convergence process. Okay? We will often choose a routing protocol based on its ability to converge. Some routing protocols converge faster than other routing protocols. RIP is a pretty crappy routing protocol. It takes a lot of time to converge. It could potentially take up to 240 seconds to converge. It's a very blingy charging cable there. You guys see that? It's supposed to be like a float. It's just flashing.
It's Christmas lights.
Interesting. Are they durable? I mean,
Yeah, I got it for like,
I always buy these cheap charging cables and then they break and.
Or they stop working after about 2 weeks.
Yeah.
I paid like $10. I got some.
Yeah.
I wanted something else.
I've never seen that before. It's fun. So convergence, we're going to choose a routing protocol based on its ability to converge quickly. The fastest converging routing protocol that exists today, assuming you implement it correctly, is actually EIGRP. EIGRP converges even faster than OSPF, if it's done correctly. OSPF is not very far behind though. OSPF pretty much, you can kind of consider OSPF to be just as fast. Right? There are some significant differences between the two protocols, but both EIGRP and OSPF converge very quickly. RIP doesn't. RIP is a slow protocol. All right? It can converge quickly, but in most cases it doesn't converge very quickly. BGP converges extremely slowly as well, but the reason BGP converges slowly is by design, because BGP is working with very, very large data structures. So the makers of BGP decided to make it so that BGP converges slowly. All right? There are generally two things that we consider when we're trying to pick a routing protocol for our enterprise. Number one, how quickly does it converge? And number two, how scalable is the protocol? Scalability meaning how large can my network get? All right? There are some other options we might look at, ease of configuration, stuff like that, but all right? So here's that chart that we were talking about. We kind of took a look at this chart from the very first slide in this chapter, the genealogy of our routing protocols. So within the concept of routing protocols, we have exterior and interior. BGP is presently the only used exterior protocol. It's a protocol that we use to route the internet, essentially. And then we have two subclassifications of our IGP protocols, distance vector and link state. RIP and IGRP are distance vector. RIP version 2 is distance vector. EIGRP kind of gets a bad rap, because distance vector routing protocols, We already know that RIP and IGRP are bad, right? Why are RIP and IGRP bad? Because they're classful. That's right. RIP and IGRP are bad because they're classful. So EIGRP, kind of by association, being that it's a distance vector protocol, kind of gets a bad rap because everybody thinks, well, distance vector protocols are not as good as link state protocols. But actually, EIGRP, even though fundamentally it's distance vector, it does take a lot of characteristics from link state. That's why EIGRP is often considered to be an advanced distance vector protocol. Fundamentally, it's still distance vector. The algorithm is a distance vector algorithm. How far is the network and in what direction do I need to go to get to that network? When we get into those protocols in more details, you'll understand why EIGRP is considered enhanced as opposed to just standard distance vector. Now I'm using these terms, distance vector, link state, you see path vector as well, but you guys have no idea what that means, right? Most people don't. They may have seen in a book that RIP is distance vector, or they may have seen in a book that RIP is link, or OSPF is link state, but they don't know what it means to be distance vector or link state. So I'm going to describe that to you guys here in a little bit. It's not on the test. You don't need to know the genealogy of routing protocols on the exam, but it is important fundamentally as an engineer to understand what you're getting when you implement a routing protocol. All right? Distance vector routing protocols, for the most part, are generally considered to be less knowledgeable than link state routing protocols. Okay? There's a plus and minus to that. Because link state routing protocols have much more detailed data structures, what does that mean from a processing perspective? They require more CPU and processing power. OSPF takes up more resources than EIGRP. The plus side to link state is that they make better decisions, or they tend to make better decisions on how to reach destinations. I'm going to describe this process to you guys because I really want you to understand fundamentally the difference between distance vector and link state. Even though it's not on the test, you know, I want you guys walking out of here thinking that you're network engineers and not just a network technician. All right? You guys understand the difference, right? A network technician knows how to implement something but doesn't know how it works. A network engineer knows how it works. All right? So there is a big difference between implementing EIGRP and actually knowing how EIGRP works. All right. So RIP version 1, RIP version 2, IGRP, EIGRP, all considered to be distance vector protocols. Well, we already know RIP version 1, first generation legacy protocol, Classful, very crappy protocol. RIP version 2, Classless, but that's the only positive thing it has going for it. It's still relatively a crappy protocol. Why are RIP version 1 and RIP version 2 considered to be inferior protocols? What is the one thing that makes those protocols inferior?
They only look at the number of hops.
Metric. That's right. They don't really understand the best path. They consider the evaluation criteria for choosing a best path is very poor. All right? IGRP was a great protocol for its time because of the metric. The metric is very complex in IGRP. Bandwidth is a major component of that metric. So IGRP already had a leg up on RIP because the metric was much better, but IGRP is classful. It didn't understand subnetting, so it has become obsolete. EIGRP is the predecessor, the follow-on protocol. The predecessor would be the previous protocol, right? EIGRP is the post-cessor of IGRP. That's not a word, but
Successor.
The successful, yes. Okay. All right. So EIGRP came out, and of course, EIGRP is very, very close to IGRP. There are some enhancements, but the biggest enhancement was that EIGRP supports subnet. Okay? So what does it mean to be a distance vector protocol? Distance vector means literally the direction and the distance. Now, when you think about routing to a network, aren't those the things that we concern ourselves with? How far away is the network, and in what direction do I need to go to get to that network? Right? You say, well, that should be any routing protocol. That's what we should consider. How far away is the network, and in what direction do I go to get to that network? Link state does the same thing, it just does it better. We'll talk about that. I promise. It's coming. Hey, how about that? It's right here. Okay? So I need to sit down and do some drawings on this one because I really do want you guys to understand the differences between these two types of classifications. All right? So let's go ahead and talk about this from the perspective of, in both cases, it's going to be from the perspective of router 1. All right? And router 1 is trying to reach this network over here, 10.0.0.0. Now, ultimately, whether it's a static route, an EIGRP route, an OSPF route, a BGP route, any kind of route, what is the goal of a route in a router?
Move data.
Well, to move data, but to where?
Closer to its destination.
To the next router, right? So that's one thing I want you guys to take away from this. It doesn't matter what method you're using. Every single routing method, the end result is the same. Where do I need to send the packet to get to a destination? Okay? So whether it's link state or distance vector, that is still the end result. R1 is either going to send the traffic to R2 or it's going to send the traffic to R3. Does that make sense? Even if it was a static route, that would be the case, wouldn't it? I would either send the traffic to R1, or excuse me, to R2 or R3. The way that that information is obtained is where the difference comes in. So as a distance vector protocol, let's say I'm running EIGRP in this top network. Let's assume that R1's only concern is to get to this 10.0.0.0 subnet. I don't need R1 to be able to reach any other network except for 10.0.0.0. Naturally, R6 has a connected route to 10.0.0.0, right? And as the owner of that route, it's going to advertise that route to its neighbors with a metric. Okay, so far so good. R4 is going to make a decision on how to get to this 10.0.0 network based on the information it receives from its neighbors. So, R5 is going to advertise the 10.0.0 network to R4 as well. So R4 actually has two different paths that it can choose to get to the 10.0.0 network. You guys agree? All right. So far, so good. How is R4 going to choose which path to use? Well, there's a metric for this path, and there's a metric for this path. Whichever one has the lowest metric, that's the one that I choose. Got it? So let's say R4 chose this path. So now R4 has a route to the 10.0.0 subnet. R4 is then going to advertise that network to its neighbor. What metric is R4 going to use to advertise that route to its neighbor? It's going to use the metric based on the path that it chose. Does that make sense? See, R4 is not going to advertise to R2 that it has two paths. R4 is simply going to advertise a single path with a single metric. It's going to say, you can come to me to get to the 10.0.0 network, and by the way, if you come to me, it's going to cost you this much. Makes sense though, doesn't it? Because we're trusting that R4 would have chosen the best path based on its metric. So R2 should be also making the same decision based on the information it receives from its neighbor. Because R2 is going to get a route from R5 as well with a metric. You guys follow me, right? All right. So R2 has two paths. Actually, technically R2 has three paths, but we'll just use the two. R2 has two paths to get to the 10.0.0 subnet. It can go to R4 or it can go to R5. Make sense? So R2 is going to choose a path. What is it going to advertise to R1? It's going to advertise the network with a metric, and that metric is going to be based on the path that R2 chose. R1 is not going to know that there are two ways to get there. It's not going to know that R4 has two ways to get there. In the end, what does R1 actually know about? It knows about, I can get to that network through R3, or I can get to that network through R2. R3 has metric X, R2 has metric Y, and I'm going to choose to go to R2 or R3 based on whatever the lowest number is. Does R1 know anything about any of the links in between? It knows the direction and it knows the distance. That's it. It has no visibility about all these other paths because those other paths were not advertised to R1. Only the destination network was advertised to R1 through the exchange of routing information. This is a term called routing by rumor. R1 makes its routing decision based on what it hears from its neighbors. So it has to trust the information that it gets from its neighbors. Now you might look at this and go, well, okay, fine. It's going to choose the best path because the neighbors are choosing the best path. Well, that may not always be the case. You can manipulate a router to choose a different path. As an engineer, for example, I can manipulate path selection from router 2. I can say, well, router 2, I want you to go this way to get to the 10 network, even though it's worse than this way. It's called policy-based routing. The route that router 2 chooses is the path that gets advertised, regardless of whether or not it's the best path. So with routing by rumor, we're trusting that the neighbor router is picking the best path. So far, so good. You guys understand the concept in general, right? Again, you're not tested on this, but it is kind of useful to understand the difference between these two methods. Link state protocols are completely different because what happens in a link state protocol is all links get advertised. That's why it's called link state. R6 does not just advertise the 10.0.0.0 subnet. R6 advertises to its neighbors the 10.0.0 subnet plus every other link that it's connected to. And then R5 passes that information on to its neighbors, plus all the links that R5 is connected to. So by the time I get to R3 and R2, there is a database of every single link between every router down to the 10.0.0 subnet. That goes into something called a link state database. By the time I get to router 1 has a complete picture of every path that exists in this network. That's why the databases in link state protocols are much larger, because the routers store all link information. Now, if router 1 wants to choose how to get to the 10.0.0 subnet, does it have to rely on what the neighbors chose? If it has a complete picture of the topology, can it make its own decision on how to get to that destination? It can say, well, I could go this way, and I could go this way, and I could go this way, and that's going to cost X. Or I could go this way, and this way, and this way, that's going to cost Y. But it's making its path decision based on understanding all of the complete paths as opposed to just what the neighbor tells it. All right? That is the difference between a link state protocol and a distance vector protocol. Link state protocols have a complete picture of the entire topology, whereas distance vector protocols only understand what the neighbors tell them. Ultimately, like I said, R1 for link state is going to choose to go to R2 or it's going to choose to go to R3. Just like distance vector, R1 is going to choose to go to R2 or R3. Okay? There's another analogy that a lot of books will refer to. It's this concept of road signs along the roadway. The analogy is, if you're distance vector, this is what you know about how to get from here to New York. You go out to the highway, you see a sign that says New York, 400 miles. You follow that sign. Do you know what's included in that 400 miles? No. But you know the distance and you know the direction. And you keep driving down the highway until you see another sign that says New York goes to the right, 200 miles. So distance vector is like signposts along the path. Link state is like pulling out a map, or for those people that actually live in this century, pulling out your GPS, seeing every single path that's available, and making a decision on what direction you want to go based on understanding the entire path. That's the fundamental difference between distance vector and link state. Ultimately, like I said though, the goal is get the packet to the next router. There's no difference ever in any routing method of how we route a packet. It's always, always, always route the packet to the next router. How we make that decision is what's different. Okay? All right. So with regard to distance vector, of course, we know that distance vector routing protocols generally don't have as much knowledge about the network now. EIGRP is the same, by the way. EIGRP does routing by rumor, just like RIP, just like IGRP. The enhancements to EIGRP are in how it converges and how it exchanges information. Fundamentally, it's still distance vector. There are a couple of other limitations of distance vector protocols, like, for example, RIP version 1 and IGRP. They used this address to exchange routing information. What are routers supposed to stop? They're supposed to stop broadcasts. But yet, the two pink boxes there, those protocols used to exchange routing information with broadcasts. All right, so that's very inefficient. At least with RIP version 2 and EIGRP, we use multicast instead of broadcast. So that's one of the changes that we saw with these two protocols. They stopped using broadcasts and they started using multicast. Here's another fundamental problem to RIP though. RIP sends out updates on a periodic basis. When should a routing protocol send out a routing update? When something changes. That's the only time a routing protocol should send out an update is if something changes. RIP doesn't do that. Every 30 seconds, RIP sends out an update. What should be sent out? If it's efficient, what should I be sending out? Only the changes, right? RIP doesn't do that. RIP sends out its entire routing table every 30 seconds. So it's very inefficient in that regard. And by the way, that applies to both RIP versions. They both do periodic updates every 30 seconds. IGRP did periodic updates every 90 seconds. EIGRP does incremental updates. It only sends out updates when they're necessary, and it only sends out updates, the update information. It doesn't send out its entire database. That's where the enhanced part comes in. That's where the advanced part comes in. EIGRP took those characteristics from link state. The periodic updates are gone. We're doing incremental updates, and we're only sending out the changes. We already talked about this concept of classful versus classless. A classful protocol, bad. We want our protocols to be classless. All right. I'm not really talking too much about that because we've already talked about that quite a bit. So here's kind of a breakdown of each of these protocols and how they compare to each other. BGP is not on here because it's not an IGP. All right? Well, you get the idea. The legacy protocols are slow, small, and generally not very efficient. Right? EIGRP, extremely fast to converge. OSPF is fast. There's a very slight difference between those two values, though. OSPF generally is considered to be as fast as EIGRP. Of course, the network domain is only as efficient as you implement it, right? If you don't implement the protocol correctly, it's not going to work very well. Scalability. There's a big difference between OSPF and EIGRP in this case. OSPF pretty much scales to a limitless size because of its design. OSPF uses a hierarchical structure called areas, which enhances its design, makes it very, very scalable. What do we mean by scalability, by the way? Network density, network diameter. How many routers can I have, and how far can those routes go? VLSM, that's a term that you probably haven't seen before. VLSM stands for what? Variable length subnet masking. Subnetting. RIP version 1 doesn't do subnetting. IGRP doesn't. Everybody else does. As far as resources go, I guess it kind of makes sense that our more advanced protocols are going to require more resources because they have much more detailed databases. Implementation, RIP, IGRP, very simple to implement. EIGRP is actually relatively simple to implement, but with the enhancements of EIGRP, like the EIGRP stub routing features and wide metric features and so on, it can get a little bit more complex. All of these protocols are relatively easy to implement in a small environment. They get more complicated when you start to get into a very large environment. For example, OSPF. when you implement OSPF, you can implement OSPF in a single area design. But you can also implement OSPF to where you have multiple areas, and you might have the backbone area, you might have a normal area, you might have a stub area, a totally stubby area, a not so stubby area, a totally not so stubby area. We don't do all that in this class. We learn all about those area types in the CCNP class. But we're going to implement OSPF, but we're going to implement OSPF in a single area design. Okay? The last line here, you definitely are going to need to know this for the exam, second exam, the algorithms that are used by each protocol. We're not going to really talk too much about the Bellman-Ford algorithm because it's pretty crappy. We are going to talk about the diffuse update algorithm, and we're going to talk about Dijkstra's algorithm, which, by the way, Dijkstra's algorithm was not designed specifically for OSPF, but it was adapted to OSPF. It's called the shortest path first algorithm. We'll see that later on. All right. You guys find this interesting at all? Yes? No?
Amen.
When we get into the protocols, it gets even more interesting. We already know what a metric is. We talked about that before. A metric is how a router determines the best path to a destination, how it evaluates the overall cost. Yeah, Dijkstra's algorithm is used in programming languages. It's used in ISIS. It's used in OSPF. It's actually even used in spanning tree. Technically speaking, the algorithm in spanning tree is Dijkstra's algorithm because it's the shortest path first algorithm, right? But yes, Edsger Dijkstra kind of came up with this concept of calculating the shortest path based on a tree structure, where you have the trunk and you have the branches and you have the leaves, and we would always figure out the best path based on navigating through those branches and trees and leaves and trunks and leaves. We'll get into that. Actually, we're not going to get into that too much in this class, but that goes into more like theoretical concepts of just calculating paths. Okay. All right, so let's wrap up this chapter by breaking down individual protocols. I'm going to point out several different components of each of these protocols. You are going to have to know this for the exams. All right, RIP next generation, that is the V6 version of RIP. It's based on RIP version 2. RIP has an administrative distance of 120. Routing updates are sent every 30 seconds. RIP sits on top of TCP. UDP, excuse me. I meant to say the transport layer. The reason why I specifically mentioned that is because there's only 2 routing protocols that actually use the transport layer, BGP and RIP. It's not on the test, but it's interesting to know because EIGRP, OSPF, and ISIS don't use transport layer functions. Okay? BGP uses TCP and RIP uses UDP. So a couple of the limitations of RIP. First of all, scalability. RIP routers can only go up to 15 hops away. The 16th hop becomes unreachable. So as far as the size of our network goes, we can't have a network that goes further than 15 routers away. Now, believe it or not, in most modern networks, that's pretty sufficient. Because we're not talking about the density of routers, we're talking about the diameter of routers. Think about a chocolate chip cookie. The density of chocolate chips doesn't necessarily determine the diameter of the cookie. See what I'm saying? You can have more chocolate chips in the cookie that's more dense, but the diameter is still how many chocolate chips do I have to go across to get to the other side of the cookie, right? So when we talk about hops, we're talking about the diameter of a network. We're not talking about the density. EIGRP, conversely, up to 100 routers in diameter. So significantly larger. OSPF, there is no limit. No practical limit anyway. I'm sure there is some sort of limit, but no practical limit in today's technology. RIP version 1, that's our old version of RIP. We can see why it's crappy, because it doesn't do anything, right? It doesn't support subnetting, doesn't do classless routing, doesn't do summarization, doesn't support authentication. Sends its routing updates using a broadcast address. Whereas RIP version 2 and RIP next generation, great. They support the LSM, classless routing, summarization, and authentication. So you look at this and say, okay, well, these are good protocols, right? RIP next generation, RIP version 2, those are great protocols because they support all these features. But they don't because of this. Hop count as the metric. That is really the downfall to RIP. The metric that it uses is grossly inadequate, especially in modern networks today. EIGRP versus IGRP. Oh, I forgot to mention, because this is on the test. In IPv6, RIP next generation, we use FFO2:9 as our address to send updates, and we use 224.009 in IPv4. They specifically ask about FFO2:9 on the second test. I'm not sure why, but I guess this is just kind of one of those things that they ask about. EIGRP versus IGRP. You're going to see a lot of similarities here because these protocols are very similar to each other. At least IGRP is. They use a composite metric. Okay? Now, by definition, a composite metric means there are several different variables that go into calculating the metric. It's actually a relatively complex metric. It's K1 times the bandwidth. The bandwidth is actually calculated as 10 to the power 7 divided by the bandwidth in kilobits per second. It's the worst bandwidth along the path to the destination. Times K2 times something, K3 times something, K4 times something, K5 times something. We'll see the metric later on for EIGRP. It is a very, very complex metric, but the more complex the metric, generally the better the decisions being made, right? We call those data points. If we have more data points to make a decision, generally the decision is a better decision. So the metric for EIGRP and IGRP is a very good metric, even though mathematically it's rather complex. We're going to learn how that metric works later today or probably tomorrow, depending on how far we can get today. We only have about 10 slides left in ICND 1, so we'll probably at least get an introduction to EIGRP, and we'll do the implementation probably tomorrow. Okay? Looks very similar to RIP version 1, doesn't it? Very similar to RIP version 1. Multicast address for EIGRP is 224.0010 or FFO2:A. A is hex for 10, isn't it? Okay. A couple of other points. What does this mean? Bounded triggered updates as opposed to periodic updates. What does it mean, bounded triggered updates?
Change your network, trigger that.
A change in the topology triggers an update to be sent. Bounded means we're only sending it to who needs that information. We don't send it to all of our neighbors, we send it to the neighbors that need the information. All right? There's a topology table that gets maintained in EIGRP. Do you guys remember what goes into the topology table? That was one of the 3 data structures we talked about. What goes into the topology table? In general, everything I've learned. goes into the topology table? What goes into the routing table?
The roster.
What I'm using. You guys understand the difference between everything I've learned and what I'm using, right? I can have 5 or 6 different ways to get to a destination, but I'm only going to use one of them. Administrative distance of EIGRP is 90. I should have EIGRP listed here because IGRP is not 90. IGRP is 110. But because this protocol is deprecated, we're really just talking about EIGRP and runs over protocol 88. IGRP doesn't actually run over protocol 88 either. So those last 2 bullet points only apply to EIGRP. Everything else applies to both. Okay? By the way, we don't have a table for OSPF, but if I did have a table for OSPF, this is what it would look like. There's only one type of OSPF in IPv4. It uses cost as a metric. Cost is a calculation of a relation to bandwidth. It uses 224.005 and 224.006 for updates, and it has all the same green check marks. So, OSPF runs on top of protocol, or is protocol 89. EIGRP is protocol 88. So what the 88 references is the protocol ID for EIGRP. So if you take a Wireshark and you're capturing EIGRP datagrams, you're going to have a data link layer header, you're going to have an IP header. The IP header protocol field points to 88 because the next header is an EIGRP header. So 88 is the protocol ID for EIGRP. Kind of like 1 is the protocol ID for ICMP, and 6 is the protocol ID for TCP. OSPF is protocol 89. All right. So we have one chapter left. Looks like you guys, we still got about 30 minutes or so left. We might go a little bit longer than 30 minutes, so let's just keep moving forward here. This one is actually a pretty fun chapter because we're pretty much just going to do a lab together. Okay? The way that I do RIP is I teach you RIP while we implement it. Because first of all, we've already learned pretty much all about the theory of RIP. You know, we haven't learned about the hold down on theory of RIP.
I don't understand theory of RIP.
I have the Siri talks to me when I say, hey Siri. And then I said theory, so she thought I said Siri. All right. Okay? So,
What does she call you?
Cisco. Yeah. Cisco. Okay. So RIP, the Routing Information Protocol. What I need you guys to do is we're going to be implementing RIP in our topology. This is our topology. We're going to implement RIP. And the way I do this chapter is we do the implementation, and then we talk about why you did that implementation. The reason why this is important, it's not important for the test, but the reason why this is important is because almost all of our routing protocols have very similar implementation techniques. So by learning how RIP works, we're actually learning how OSPF works and how EIGRP works, at least the implementation piece. Now, you have to remove your static routes. Why do you have to remove the static routes before we implement RIP?
Because you don't have the routes. We use them routes.
Static routes have an administrative distance of 1. RIP has an administrative distance of 120. So if we leave the static routes in, they're what's going to show up in the routing table, The RIP routes will not show up in the routing table. So the first thing I need you guys to do is remove your static routes.
Work, just everything working.
If you didn't save, yeah, if you didn't save your file, you can just open up the file again without any static routes. Okay? All right. Is everybody good to go then, or do you have to remove them? Because you may have saved the file. I'll give you a couple of minutes to do that, and then we're going to do our implementation here. All right? You guys remember how to remove your static routes, right? You just take whatever command you use to implement the route, put a no in front of it, and that will remove the route.
Okay.
So if you do a show run, you shouldn't see any IP route statements. That's basically it. All right?
This is going to be implementing what again? The IGRP?
We're going to implement RIP.
RIP.
Yeah.
Version.
Well, we're going to start with 1, but, okay?
Got it.
All right, so let's talk about implementing RIP now. Okay? So here's what we're going to do. I want you guys to go into each of your routers, router 1 and router number 2, and I want you to duplicate what you see on the screen here. Go ahead and just put those configurations in. We're going to talk about what they do after you've done it. But this is kind of an interactive exercise where you kind of do the thing first, and then we talk about why you did that as part of the discussion in the exercise. All right? So just duplicate exactly what you see here for router 1 and exactly what you see here for router 2. That should only take you about a minute. And then we'll talk about why you did those commands and what those commands do. All right? Oh, that's literally 2 points, 3 points. I've seen somebody get an 803 before. 801 is pretty close too.
Which was kind of, it's only 3 points away too.
Yeah. Technically, they're not supposed to be working this year. I know you're like just dying to go take it again right now, right? You're like, I'm going to take it again right now.
Also, crazy because the Conti is like that.
No, you have to wait 5 days. Yeah. I mean, the only option is to go take the other test, the newer one, but it's going to be completely different questions.
So that's easy.
Yeah. Okay, I don't know how many of you guys online are actually going through the process here, but if you're not, if you are doing the configurations online and you're not done, let me know. I'll make sure that I don't want to leave anybody behind. Okay, I'm assuming that Bernard is probably doing it, Giovanni's probably doing it, Yasmina's probably configuring it. Looks like Michelle's participating from her mobile device, so she's probably just watching. That's fine. Okay. You good to go?
Yeah.
You good to go? Not yet? You good to go?
Sorry.
Okay. Bernard, you good to go? Giovanni's good to go. Bernard's good to go. Great. Okay. We got a couple of slow typers here in class, so we'll let them catch up. You're good to go? You're good to go. All right. Let's talk about what you did, right? Because that's really important. And the reason why this particular slide is important, because when you want to implement OSPF, you type router OSPF. When you want to implement EIGRP, you type router EIGRP. We use network statements in OSPF. We use network statements in EIGRP. So even though we don't really care about RIP, we need to understand what these commands do, because by understanding this, we actually get some understanding about how EIGRP works and about how OSPF works. So the first command that you guys entered was router RIP. Router RIP, and if you notice you hit enter, it takes you into config-router. So by executing router RIP, you're not actually turning on RIP. You're just going into RIP configuration mode. So when you type router OSPF, you're going into OSPF configuration mode. When you type router EIGRP, you're going into EIGRP configuration mode. That's the only thing that command does. It basically is like going into an interface to configure interface properties. The only difference is we're configuring the properties of RIP instead of properties of an interface. What actually enables the protocol, what actually turns on the protocol, are the network statements. The network statements are very, very important. In IPv4 for RIP, EIGRP, and OSPF, we use network statements. Even in BGP, we use network statements. All right? So, let me ask you guys a question, because this is where people get the most confused about a network statement. Technically speaking, on router 1, which interface do we really need to run RIP on? What is the purpose of running RIP in the first place?
To know about all the more.
To give us the chance to exchange routing information with another router. You guys agree with that? It's a language that allows two routers to talk to each other and exchange information. Based on that definition, technically speaking, which interface would you assume is the only interface we need to run RIP on? The serial link, right? The one that goes to the other router. Okay? But that's actually not the case. The network statement does two things. It does tell the router which interface to run the protocol on. But it also tells the routing process which networks to advertise. This is confusing, I understand, but let's just take router 1 for example. Router 1 has 3 interfaces. Let's assume that on the Ethernet sides, there are no routers. So you might say, well, I don't need to run RIP on those Ethernet interfaces because there's no routers on those interfaces to exchange routing information with. If I leave out the network statements for those Ethernet networks, then RIP doesn't know that they exist, and RIP will not advertise those networks to router 2. You understand the difference now, right? Two things that a network statement does. It tells the protocol, or tells the router, which interface to start sending updates out of. We don't need to send updates out to Ethernet interfaces. There's nobody there to hear them. So we don't put network statements for that purpose on those interfaces. But it also tells the router which networks to advertise. If I left out the network statements for my Ethernet networks, those networks would not be advertised. You follow me? Okay. And by the way, that's the same for OSPF, and it's the same for EIGRP. Which is why we have 3 network statements for router 1. Now, there's another kind of twist to RIP. Network statements are entered classfully. It's not because it's RIP 1 or RIP 2. It's just how we enter the network statements. That is why you only have 2 network statements for the router on the right and 3 network statements for the router on the left. There are 3 Class C networks on the router on the left. There is 1 Class C network on the router on the right and 1 Class A network. So essentially, by putting in a network statement of 10.0.0.0, 10 is Class A, right? We're telling the router any interface that starts with 10 is part of RIP. Any interface that starts with 10 is part of RIP. Okay? Why didn't I put in 209, 165, 200, 224? 224 is the actual network on the serial link. Why did I not put 224? What class is 209?
Class C.
Class C. So the only thing that matters are the first 3 octets. Now, very important to understand here. By putting a network statement of 10.0.0.0, you're telling that router any interface that starts with 10 is running RIP. Any interface. All right? That's it. You've configured RIP. You can now route between these 2 routers, these 4 networks. Okay? But there are a couple things we still need to do. It is literally that simple to implement a routing protocol. By the way, EIGRP, you can do it exactly the same way. Classful network statements, router EIGRP. The only difference is you pick an autonomous system number. So even though EIGRP is a very complex routing protocol, implementation is relatively simple. Of course, I'm going to teach you all of the advanced stuff as well, so you're going to learn a lot more. But there are a few problems with this implementation. All right, so we're going to break that down. Everybody go into router 1, okay, and type show IP route. I'll just do what's on the screen here. Show IP route RIP. Let's go ahead and analyze this output so I make sure you guys understand. You should see exactly what you see up on the screen. If you don't, we need to figure out why. Okay? Obviously, we know in this case we're looking at the routing table. We're looking specifically at the RIP routes. R is how the route was learned. 10.0.0.0/8 is the network. Well, that's a little bit of a problem because I'm not seeing the subnets. I'm only seeing /8. We'll find out why in a second. What is the 120 in the brackets?
Administrative distance.
That's the administrative distance of RIP. What is the 1? The metric. So from R1's perspective, it costs me 1 hop to get to the 10 network. What is the via address? 226. Next hop, right? Remember, routing is always about, if you want to get somewhere, where's the next router I have to go to get there? Agreed? So 226 is the next hop. 3 seconds is how long the route has been in the table since the last update. So that 3 seconds always goes back to 0 every 30 seconds because the route gets updated every 30 seconds. Does that make sense? What is serial 000? It's the exit interface. It's the interface I go out of to get to 226. Why is it that router 2 shows both subnets, but router 1 only shows one network?
Two different classes.
Well, 10 and 11 are Class C. They're separate Class C subnets. 10.1.1.0 and 10.1.2.0 are subnets. This is classful behavior. This is how a classful protocol operates. It doesn't send out subnet information. 10.0.0.8 is the classful representation of 10.1.1.0 and 10.1.2.0. So what version of RIP do you think we're running? Version 1. The default version of RIP in a Cisco router is RIP version 1. All right? There's a way to verify that, by the way. A new command that you guys are going to learn. Let's go into router 1. By the way, this command is like show IP interface brief for routing protocols. We use this command all the time when we're verifying routing. Show IP protocols. If you're verifying routing operations, this is one of the commands that you're going to use constantly. Basically, it's not a command specific to RIP. It's a command that's used to verify any routing. In this case, it's giving us the RIP information. Updates are being sent out every 30 seconds. The next update goes out in 12 seconds. All the timers for RIP. Invalid timer is 180 seconds, hold down timer 180, flush timer. I'm not going to really get into those timers. By the way, those timers are tested on the second test, but I really don't want to get into it. It's not really that important, practically speaking. Okay? What version of RIP am I sending? I can see which interfaces are running RIP. Gig 00, Gig 01, Serial 000. They're all sending version 1. They can receive both, but they're sending version 1. Automatic network summarization is in effect. We'll talk about that in a second. That's a pretty crappy thing that RIP does as well. What is maximum path 4? What does that mean? Maximum path 4. That is the maximum number of paths that RIP will load balance over by default. If we have 5 paths that with the same metric to a destination, we're only going to put 4 in the routing table. And then we see our routing for networks. We see our neighbor information, 226 with a distance of 120. The last update was received 5 seconds ago. So you can see that this is a pretty useful output here. Okay? Pretty useful output because it gives us all of the general properties of our protocol. So I guess the first thing that has to happen is we need to stop using version 1 and we need to start using version 2. All right. But before we do that, I want to show you guys one other thing. It's called a debug. Debugs are different than show commands because debugs give us real-time information. Show commands are only a snapshot in time. So everybody go ahead and go to router 1 and run debug IPRIP. And you'll see what will happen is you'll start to get these messages that pop up. They might not happen right away. It just depends on what cycle, what time you're in your cycle of sending and receiving updates. But eventually you'll see some pop up. And it's basically all of the updates that you're getting and all the updates that you're sending. The point of this is that it's very inefficient. It's inefficient because the router keeps spewing out information every 30 seconds when it doesn't really need to. The nice thing about this debug is it shows us the version of RIP that we're running. It shows us which interfaces are sending and receiving RIP updates. It even gives us the metric information. Look at the second block in this list here. Why is the metric 2 for the 10.0.0 subnet? Why is the metric 2 for the 10.0.0 subnet? 2 hops, right? Well, look where that advertisement is going out of. It's going out of the gig interface. So essentially this router is saying to anybody on that gig interface, if you want to get to the 10 subnet, it's 2 hops away. It is 2 hops, me and the next router. So it's taking the metric it's getting from the neighbor, it's adding itself into that metric and sending it on its way. Okay? If you want to turn off, we do want to turn off our debugs because we don't want them to keep going. Just type U space ALL. U space ALL. Not YOU, just the letter U. That stands for undebug all. You could also do a no debug IP RIP, but undebug all turns off all your debugging. Be very careful with debugs, by the way, because debugs are very processor intensive. If you run the wrong debug, you crash the router.
Debug all the core.
Debug all is a bad command. Yeah, I don't know why it's even an option. When you type debug all, your device will crash within a second or two. It even gives you a warning and says, are you sure you want to run this? And then you say yes, and then the router crashes. Another one that's pretty bad is debug IP packet. That's pretty bad. But there are a lot of debugs that can be very detrimental to a platform. Remember, debugs are us capturing information in real time. Okay. All right. Well, let's go ahead and switch to RIP version 2. I think it's pretty self-explanatory what we're doing here. We're not running RIP version 1 anymore. We're going to run RIP version 2. So you go into router RIP and you type version 2. Let's go ahead and do that on both routers. Okay. So that's how we switch from version 1 to version 2. We simply type version 2. We don't have this option in OSPF or EIGRP, by the way, because OSPF and EIGRP don't have versions. So this only applies to RIP. How's the audio, Bernard? Is it okay? Giovanni, you're going to type in, not in config mode, in global and privilege mode, U space ALL. The letter U space ALL. You could do if you're in config mode, yes. If you're in config mode already, type do you all. That sounds like a bad country song. Did you get it to stop, Giovanni? No. I'm not at my keyboard. Bernard, you want to go ahead and put that in the chat window there?
It's a southern term.
Yeah. In the United States, you all means, hey, what's up? Yeah. If you're in the subway.
Everyone.
U stands for undebug. All stands for basically turn off all debugs. Okay? Make sure you're in the right mode of operation, Giovanni, when you type that. All right. Yes, you can also do a no debug IP rip, and that will turn off that specific debug. So, we've now switched to version 2, so that means everything is happy. We should see all of our routes, right? Go into router 1 and do a show IP route. Still 10.0.0.0/8. Yes? We're still not seeing the subnets, even though we're running RIP version 2, which is classless. Well, guess what? There's this little feature in distance vector protocols called automatic network summarization. You see it right here. If you run show IP protocols, you'll see it is in effect. Basically, what the makers of distance vector protocol said is, let's make the protocols classless, but let's make them act classfully by default. The idea was to make it more efficient, right? To automatically summarize to major network boundaries. But in most modern networks, that causes all kinds of problems because we're summarizing to major network boundaries, which means the only way that would ever work is if all those networks are behind that router. It's a bad, bad thing. In fact, in Cisco, EIGRP used to do the same thing. It doesn't anymore because in the new version of Cisco, they turn that off automatically. Okay? So it's not that we're not getting the subnet information. If you were to actually do a debug now, I don't want you to, but if you were to do a debug now, you would actually see the subnet information, but it's being summarized to classical boundaries. So that is something that we have to turn off. We need to turn off that automatic summarization. Single command, no auto-summary. So let's go ahead and implement that in our routers. That turns off that automatic network summarization feature. I use the word feature loosely here because it's not really a very good feature. Okay, no auto summary. You would never implement RIP without doing this. There's really no reason to ever have automatic network summarization. And if you go look at your routing table, you'll now see your subnets. You'll still see the /8 because RIP is dumb. It's going to hold that route for 240 seconds until it finally determines it's no longer needed, then it will drop it. That route goes into something called a hold down state, where it basically stays in the routing table for a period of time.
How come I saw them before I did the no auto summary?
You shouldn't have seen it. Well, you might have seen it before if you were in the wrong router, but they would have been shown as connected routes.
Okay, you're right. Never mind.
Okay? So we're tuning RIP, right? We implemented RIP with one slide, but basically what we're doing now is we're applying best practice standards to the implementation of RIP. We're going to do the same thing with EIGRP and OSPF tomorrow. We're going to configure EIGRP and OSPF, and then we're going to tune those protocols to make them more efficient. So you can see we're now running RIP version 2. By the way, the versions are not really compatible with each other. So you can't run version 1 on one router and version 2 on the other router. You'll only get routing information displayed in one direction. You have to be running the same version of RIP. So now I see all my subnets. Great. We're basically done. But there are a couple of other things that we need to do. How about this? Passive interface. You guys are tested heavily on passive interface on the second exam. Several questions about passive interface. If you consider what's happening with RIP, based on how we've implemented RIP in the past, RIP is sending out updates on the Gig 0 and Gig 01 interface every 30 seconds. But there's nobody on the Gig 00 interface that needs to see that RIP information. There's nobody on the Gig 01 interface that needs to see that RIP information. So we're wasting resources on those networks. In addition, we're sending out information about our routing domain that somebody can capture because all they have to do is open up Wireshark and subscribe to the multicast address FFO or 224.009 and they'll get that information. So there's a security risk. So the natural inclination would be to take out the network statements for those networks, but then those networks don't get advertised. So what they've done is they've added another command that gives us the ability to suppress updates from leaving an interface. And that's what passive interface does. It still allows the networks to be advertised, but it suppresses the protocol from running on the interface. So anytime you have an interface, and this is the exact same command in OSPF, it's the exact same command in EIGRP. If you have an interface that you don't need to send hellos out of, or you have an interface you don't need to send updates out of, make those interfaces passive so that we're not wasting resources and we don't have a security vulnerability in our network. There's two ways to implement passive. You can make an interface passive, or you can make all the interfaces passive and then make an interface not passive. So it's one or the other. You don't have to, you can choose how to do it. If most of your interfaces are passive, then you'll go ahead and do passive interface default, and then you'll make the interfaces you don't want passive not passive. If only a couple of interfaces are passive, you'll just make those interfaces passive. That make sense? What does the passive interface command do? It suppresses the protocol from running on the interface. So in OSPF and EIGRP, if you make an interface passive, you cannot form a neighbor adjacency on that interface because you're not sending hello packets anymore. RIP doesn't do hello packets. RIP doesn't form neighbor adjacencies. It's kind of a very dumb protocol. All right, so again, just to kind of verify everything, if you do a show IP protocols, you can see everything that we've done. We're running RIP version 2. We're now only running it on serial 000 because the other two interfaces are passive. You see down there where it says passive interfaces, Gig 00, Gig 01. Everything else is the same. Just the interfaces are passive. You guys don't have to run the debug. I only put the debug snapshot here because the debug will tell me that I'm only sending out updates on serial 000 and I'm sending version 2 updates to 224.009. Okay? That is pretty much it for RIP. I mean, the only thing left for RIP that we didn't talk about is RIP Next Generation. We didn't talk about how to implement RIP for IPv6. I'll probably be adding that to this course for the next go-around. And we didn't talk about authentication because RIP version 2 does support authentication. We talked about authenticating routing protocols in the CCNP class. That's it. That is officially the end of IC&D 1. Okay? But there's some stuff we covered that's part of IC&D 2 as well. So tomorrow, we're done for today.